Welcome to our short introductory course, how to get started with quantum computers and quantum computing. In this short course, you will be able to learn why do we need quantum computers, what quantum computing is about, how we can perform operations with quantum computers, the essential core math skills that's required to understand quantum computations, how we load and retrieve information from the quantum realm into our classical world, and how we can perform simple calculations using very simple quantum algorithm. This course you are gonna do by hand, so you learn more about how to do things in quantum conceptually. However, this course is gonna be followed by another practical course which will show you how to do the quantum computations and mathematical operations that we are gonna have in this course using the programming language of Python and Qiskit as a software development kit. Qiskit is an open source provided by IBM. Let's go. First, what is a quantum computer? The quantum computer is a new type of computers that uses quantum mechanics to perform computations. The quantum computer is based on the principles of quantum mechanics, which is the branches of physics that deals with the behavior of particles at the atomic and subatomic levels. With the language of quantum mechanics, we can do three main applications. We can compute with them. We also can use them to create quantum sensors and to send and retrieve informations with them in quantum communications. Quantum mechanics is a very complex and counterintuitive theory, but it has been experimentally verified and it is correct. Nothing wrong about quantum mechanics. Quantum computers are inspired from quantum mechanics that you can simulate or emulate quantum systems by another quantum systems, and this should save computational time. The idea is that when you go to simulations of large molecular systems or complicated simulations in chemistry and physics, you would require huge computational resources in order to perform such computations. This can lead you to reach the classical limit of computing in a way that at some point, the amount of RAM and the number of cores and the processors will not be enough for you to run your simulations. And hence, quantum computers can provide a solution because of the way that the Hilbert space or the space in quantum mechanics work. You can just leverage the superposition, the entanglement, and the other quantum properties in the quantum realm to perform computations in a much more efficient way. And this quantum way is suitable for executing calculations related to another quantum systems. So this is because the quantum computers can exploit the quantum mechanical properties of particles to perform computations in parallel. And in this section, we are gonna discuss this. But before we start, we need to highlight the quantum computing workflow. And the quantum computing workflow consists of the following steps. First, we have what is called the quantum state preparation. This means that the quantum computer prepares the initial state of the qubits. And then the qubits, those are the basic building blocks of information in quantum computers. They will be prepared in a specific initial state. And this initial state could be the ground state, which looks like classical, or could be initialized in a superposition of zeros and ones. Once we do this, it means that we load the initial information or we assign the initial informations to the qubit system. Then we need to perform gate operations. And in this step, the quantum computers will execute gates or quantum operations in a specific way on the qubits. The quantum gates are essential part of the building blocks of quantum circuits, and they will be used to manipulate the quantum state that's initially done on the qubits. After that, this all quantum realm, we need to retrieve information from the quantum system. And to retrieve this, we need to perform measurements. And the measurement will transform, it's like a conversion of the quantum information which we cannot comprehend in the quantum realm into the ways that we can see them classically. So the quantum computers will measure the final state of the qubits, and this measurement will collapse the quantum properties like the superposition of the qubits and turn them and convert them into classical state. And this will be used to extract the final result of the computations. Once we do this, we do classical post-processing. And in this step, the number that we have retrieved in the measurements, we are going to use it to obtain the final result of the computations itself. So that's basically the workflow. We have the qubits. Those qubits are the building blocks of information in quantum computers. We need to prepare them in a specific state. This state could be the ground state or the default state, which look like classical. All of them are zeros. Or we can initialize them with a pre-registered information. And then we prepare them in a state that could be composed of superposition and entanglement. We are gonna explain those concepts later. But once we do this, we can perform some operations using quantum gates, and those will be done in sequence. This sequence could be coming from a quantum algorithm. Once we perform those operations and we are done with them, we need to retrieve the information back. And the way we convert from the quantum realm into classical world is by performing the measurements. When we measure, the quantum state will collapse and will become like a classical state, and then we have the numbers, and then we need to use this in the classical post-processing. We need to correlate the number we are measuring from the quantum system into the numbers that we are looking for and make this conversion for ourselves, and then perform a post-processing. Like, for example, do we need to repeat the computations again and obtain like sort of a statistical answer? Do we need to make some corrections, and so on? And once we do this, we come to the final result, and the final result will contain the value of the algorithm or the classical problem that we are working on.